Hey friends, a colorful welcome to all of you once again. So today we will going to discuss about concept of electric field. Actually, we ended our last video on Coulomb's law. So from there we will start. So we know if two point static charges Q1 or Q2 are separated by a distance r, then the forces between them is directly proportional to the product of the charges q1 q2 and inversely proportional to the square of the distance, and proportionality constant comes, which is actually 4 pi epsilon naught in SI system. And to make it in vector form, we can write f vector, and it is unit vector, right? Where it is radius vector or distance vector, you can say. Okay, so yesterday or the on the last video we have not said anything about that epsilon naught or that constant. Okay, so this epsilon naught is called the permittivity of the vacuum. Naught implies the vacuum. Okay, so actually we assume that these two charges are at vacuum. That's why this constant comes as epsilon, because epsilon naught has a standard value of 8.85 into 10 to the power minus 12, and the unit you can derive from this equation: Newton inverse Coulomb square meters inverse 2. Okay, so what if we will make it in any other medium apart from vacuum? Okay, so basically we cannot every time we cannot perform those forces on vacuum, right? So there may be water, there may be air. So then we can write force equal to, this is at vacuum F0 and this is at any specific medium. Okay, say the medium is R, then 1 by 4 pi, so not R, any medium. Okay, then we only write epsilon. Okay, why epsilon? Epsilon means the permittivity of that specific medium, and this epsilon can be written as epsilon equal to epsilon r into epsilon naught. What is epsilon r? Epsilon r is called relative permittivity. Relative permittivity of that specific medium. If it is water, then it is epsilon r for water, which is 80. If it is air, it is almost 1.0 something, almost near about to vacuum. Okay, so why write like that? Because we already know that value epsilon naught. That's why we always try to make it epsilon equal to epsilon r into epsilon naught. So epsilon r can be defined as the ratio of epsilon by epsilon naught. Okay, this is this is permittivity of absolute permittivity of a medium, and this is absolute permittivity of vacuum. Okay, so next we will go to the concept of electric field. So as we all know, if two charges are there, okay, q1 q2, okay, or qq, they will realize some forces or some distraction between them, right? So we can analyze this phenomenon like that. Suppose first you place a charge q, then it will create something around it, and if we put another charge, then it will realize something. So we can say it, this is source charge, we put it here, and this creates something around this, and then we put a test charge around it. So this test charge will realize something which is called electric field. By that we can analyze the concept of force, electric force, which is Coulomb's law force. Okay, so basically electric field or electric field intensity, it is denoted by E. It is also a vector quantity, and the expression is force per unit positive charge, unit positive test charge actually. Okay, we'll say it later. The definition is like that. It is defined as the force experienced per unit positive charge on a vanishingly small. Why vanishingly small? Yes, vanishingly small. Positive test charge placed at that point. Okay. So at any point, the electric field or electric field intensity is defined as the force experienced per unit positive charge on a vanishingly small positive charge placed at that point. So it is quite complicated, right? It's appeared to be, but it is easy. Suppose let's relate with real life example. Okay, suppose you are asked to buy some rice. Okay, rice grain. So how you will buy it? You will go to the shop and ask for few kg rice. So, but what is the fundamental quantity? Why not you are saying, okay, give me that number of rice grains, okay, that tiny rice grains? Because if you say give me that number of tiny rice grains, you have to count that number and it will be huge. So you have to provide much more effort. So it is easy to say it, okay, give me just unit, a standard 1 kg or 5 kg, 5 into 1 kg rice grain or rice, right? So it will be easy to measure it with 1 kg with weight rather than counting it by grains. So it is easy to make it a unit standard. Okay, that's why we will use the concept of electric field, where we will say that electric field, a source charge will be create some electric field around it. And how to measure it? So to measure it, we will put a test charge q0, test charge around it, which will be vanishingly small or very very small to the source charge. Why? Because if it is not so, then it will also make some field or it will also force it. So the distance will be changed and it will interact with qs. So it will affect qs. But if it is very small, the effect will be very less or we can neglect it, right? So this q0 must be small. But when we have to measure it, then we have to measure it with respect to some standard value. That's why we have to make it unit, okay, to define it. Okay, so electric field actually F by Q0, but when we will define it, we will say that if Q0 equal to 1, then E equal to F, right? As we all know, that's how definition comes when it is like a ratio, right? So it is not a tough thing. Okay, next, okay, superposition theorem. We have discussed on the earlier videos the superposition theorems for Coulomb's law. It is applicable. Similarly, it is also applicable for electric field as well. Okay, superposition theorem for electric field also applicable for electric field or electric field intensities. Okay, so actually basically if there is a charge q0 or a point p and there are multiple charges around it, q2 q3 dot 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 qn, okay, then separately or individually they will create some electric field at that point p, right? E1, E2, E3, okay, En, right? So to find out the resultant or the resultant E at the point P due to all charges, we can just find out the individual electric field and just add them. Okay, they will not mutually affect each other, E1, E2, E3. Okay, dot En. That is superposition theorem. Okay, we will apply it on later on the dipole portion. Next comes to, okay, it is electric field, it's quite theoretical, right? Let's visible it. Okay, okay, just try to visualize it. Okay, so we can visualize it through the concept of electric field lines. Electric field lines or lines of force. We also call it lines of force, electric lines of force. Okay, both term are same, actually define same meaning. So what is electric field lines? So it is nothing but if you if you put a positive unit charge and if it can move freely, then the path of the charge is said to be the electric field lines. So it is the path along which a unit positive charge would move it if it is free to move, right? Okay, if it is free to move, then this will be this is lines of force or electric field lines. So the electric field lines can be straight line or curvilinear in nature. So if it is straight line, then at every point the direction of the electric field lines will be at that point the arrow. But if it is curvilinear in nature, okay, like that, then at any point, suppose in that point the direction of the electric field lines will be the tangent. The tangent, we have to draw the tangent and then we have to define it. So that direction will be the electric field lines direction. Okay, so there are some properties. Okay, one more things, the electric field lines, the strength of electric field lines, the strength of electric field or the electric field intensity, the electric field intensity is nothing but the total number of lines of forces crossing per unit area. So if at this point you have to find out the electric field intensity, so that will be the total number of electric field lines on that portion per unit area. Okay, so that will be that. So there are some properties of electric field lines. They are very important properties. First properties is the electric field lines always start from positive charge, okay, plus q charge, and always terminate in minus q charge, negative charge. Okay, so it will start from positive and it will go to negative end. Start from here and go to negative. Now what if there is only isolated positive charge? Then if that is like that, if only isolated positive charge, then the electric field lines will comes from the positive end, but it will go up to infinite. So we will assume that the negative charge is at infinite theoretically. And similarly, if there is a negative charge, then we'll say the electric field lines comes into the negative charge and it will terminate in negative charge, but it comes from infinite, where positive charge belongs to the infinite. Okay, like that. Okay, and next property, I think what was that? Okay, yes, one more important property is the electric field lines never intersect each other. That means two electric field lines, suppose that is electric field lines, that is electric field lines. Okay, if they intersect each other, we know electric field lines or electric field are just a vector quantity. So if they intersect each other, then they will make are resultant electric field lines here, which is here. So two direction of electric field line is not possible. So from 2 you are getting 1. So it is a contradiction. So two electric field lines cannot intersect each other. Okay. And one more thing is electric field lines or lines of force do not pass through conductors. Okay, that's why electric fields in between a conductor is always 0. Okay, through conductor. Why? We will came to the later part on the capacitor chapter. Okay, then we will discuss about permittivity or dielectric constant. Okay, vacuum. Okay, it is also called a dielectric constant. Dielectric constant. Dielectric constant, and this part we will discuss on the later chapter in details. Okay, to know conductor. Yes, two more important properties. One is the electric field lines, they contract longitudinally. So what is longitudinally? Actually it is lengthwise. And by these properties we can explain the that is important, explain the attraction between two unlike charges. We know opposite charges attracted each other. Okay, how? Suppose two unlike charges plus and minus. So if plus here, we know electric field lines comes from positive end and terminate in negative end. So it will be like that, it will be like that, it will be like that, it will be like that. The electric field lines will be like that. So look at the field lines, it will like that. The field lines are longitudinally here, the positive to negative end, the lengthwise. So they are just contracting each other, right? So they are just making contraction. So by this contraction we can say they are trying to attract each other, bound each other. Okay, and one more properties, they exert, the electric field line exert lateral pressure. What is lateral pressure? On each other. Okay, so what is lateral pressure? It is nothing but suppose, okay, it will lead to explain the repulsion between two similar charges. Okay, so how it is do so? Does so actually when two similar charges, let's say positive and positive, right? So we know they repel each other. And one more thing we know, the electric field lines comes from positive end, positive charge, and it will terminate in negative charge, but here is no negative charge, so it will terminate in infinite. So it cannot go to positive, so it have to bend, right? It have to be bent, it will bend, like that. Right, so the electric field lines will be like that. So look at the electric field lines. Okay, so the electric field lines here, they are trying to laterally exert pressure. Look at that, they are trying to pressure each other. Okay, pressurize each other. So they are just going out, so they are trying to repel each other. So by this explanation we can say that the similar charges always repulse each other. Okay. Okay, next okay, just okay, wait. So let's come to the next point, electric dipole. I think that will not be a problem to you. Okay, I think there is no shadow now. Okay, electric dipole. So what is electric dipole? Actually, it is a system of two equal charges, equal but opposite charges, opposite charges separated by a distance, separated by a certain distance. Okay, so two charges, two equal charges, two opposite charges, okay, minus and plus, and they are separated by a certain distance 2d. Okay, so then it is called electric dipole. So electric dipole, you can say water molecule. Okay, you already heard about it in chemistry. Water molecule can be separated by like that, water molecule H plus OH minus. Okay, right? So they both together they make water molecule H2O. So they form a dipole. Positive H plus, 1 unit positive charge, 1 unit negative charge, and their bond length. Okay, yes, one more thing here, we can say an important parameter for dipole, electric dipole, is the dipole moment, which is numerically defined as P equal to Q into 2D. Generally the direction of the dipole moment is along the radius vector or this distance. Okay, along the distance. Generally the direction of the dipole moment is always negative to positive charge. Okay, negative to positive charge. Just try to understand this or try to memorize this. You have to use it on the later part. Okay, and one more things, dipole moment, ideal dipole, the condition for a ideal dipole is these two charges are equal, so these charges have a high value, okay, with comparing to the distance. So we can say these charges almost